Well, I feel since the club has generously put forth the resources to support our being involved with the science fair, I should report back a little bit on some of the doings that got us to this point. Um, I was hoping Al Hall would be able to help me with this one this year. Al, with his expertise, is the one who can explain all the mathematics we encounter that I can't make sense of. Um, we normally, on average, we have maybe 2 students, if we're fortunate, at the Connecticut Science Fair who have done a project relative to astronomy. Some years it's been so barren that Al and I have looked for physics projects where we can sort of say, well, physics is a handshake to astronomy and a very strong one. And we've included those students as recipients, and they've had some great sharing with us. Figuring with the pandemic being such a boat anchor on everybody's life, I figured this year's, I didn't do it last year, but I figured this year would be a breeze because involvement in everything is at a minimum, it seems. Well, the bottom line is I had 10 projects, all worthy of scrutiny and consideration for this award. And I think you should, just to see the diversity of these projects, I'm just going to go down them by title. Of course, Katie's is Asteroid Occultation Measurement. Another student did one on polar alignment software for DSLR. Another one was on hidden galaxies. I might add that there was a strong component of gravitational lensing that was included so that should make sense. Another one was limb darkening effects on flares and coronal mass ejection type events.
Excuse me, Scott?
Yes.
Can I interject for a second?
Please do.
Mr. President, please stop sharing your screen so Scott can be front and center. Thank you.
I'm not sure. You should have asked my permission for that.
You're the speaker. That's what you asked for.
Okay. I'm so eager to give others the opportunity. Hidden galaxy, limb darkening effects. Another project was using binary systems to detect unseen matter. The next one was a model to determine vegetation compatibility of exoplanet atmospheres. That was a poster only. Then there was Friend or Foe, Starlink satellite releases limited to Kessler syndrome, which is inevitable collisions. I put a lot of time looking over that. There were some substance issues and depth to that I think didn't quite measure up. The other winning recipient, David Joe, the title of his project was The Core of Neptune, and I'll get back to that in just a moment. And then the last one was Exploring Artificial Gravity and Spaceflight, which had good hands-on possibility, but the science was a little foggy in this one. But that's what kept me busy through the process. I want to briefly mention, if I may, David Joe, who is a senior. I'm drawing a blank now. One moment. Johns Hopkins. He's a senior at Hopkins School in New Haven, and that has a handshake with Johns Hopkins University. But he has been accepted and is going to be entering an astronomy program at some little backwoods school known as Columbia in New York City, of course. His project actually was a large poster that had as much mathematics on it as it did descriptive material. But the title, The Core of Neptune, was a little misleading. Actually, he had found and did research through data mining on a planet, exoplanet found by the Kepler-2 project that had the characteristics of what is thought to be the core of a Neptune-like planet. Now, let me just backtrack for a little bit. In his information, he is describing how, oops, I'm getting, I just want to make sure somebody is not having trouble getting contact. Okay. He was looking for exoplanets that are few in number, and they lie between of the exoplanets that have been measured now, and there are over 4,000 of them. There are the super Earths, which lie between 1.0 and 3.9 Earth radii. And then there's a jump to what is called the super Earths, when we're looking for, I should have said when we're looking for an Earth-like planet as an exoplanet. These super Earths are considered to be like sub-Neptunes, a dense core and a dense atmosphere. Dave determined that there were very few potential Earth-like exoplanets that were within the 2 Earth radii measurement, that size. So he started crunching all this data, and there is a huge amount of data available for all this stuff. I think it becomes clear to anyone, particularly a student looking for discoveries to occur. I think most of us are familiar now that data mining is a very well pursued means for searching out and finding new information on just about anything. I mean, they're still mining data on Hubble. They're mining data on the Voyager missions. They're going to be mining data on the Kepler, the Kepler-2, and the TESS, the Transiting Exoplanet Sky Survey satellite project, which is working now. But there's going to be data for generations that's available to mine. So Dave jumped aboard one of these, and the majority of his data crunching was data measurements of radial velocity information. And from the radial velocity information, as far as information about the planet, its mass, its atmosphere, its periodic, I had no idea that radial velocity had so many overtones and information opportunities, that was a real eye-opener here. Now, to understand exactly what he did and how he did it is beyond my skill sets. But I looked over his project, looked at the depth and variety of the information and his resources. His mathematics was applied to specific aspects of this particular planet, Earth-like planet. And it's pretty interesting what he came up with his crunching. This 2 Earth radii object has 28 Earth masses. So we have what is a very metal-rich, iron-rich core with an atmosphere. And he determined from the astrometrics of this that this was that this is a type of exoplanet that was believed to have been once part of a larger object, a Neptune-like planet that was altered in various processes of the star. I will say we've seen presentations where the astrometrics of Neptune, I think it's Neptune, I'm trying to remember, we have seen where it's hypothesized that some of the large gas giant planets of our solar system may have been much closer to the sun at one time. And it's a really spectacular numbers crunch and computing that enables this model to come forth. But I was reflecting on that when I was trying to wrap my brain around this project. And I did got to have a discussion with David. I did get to meet him. And he tried to explain the best he could to clarify this to me. But the object that he concluded with these characteristics, I asked him, is this something you plucked out of something new, or has NASA been looking at this as well? And he says, yes, NASA has looked at it. This is their information. And my interpretation of what I'm seeing seems to be consistent with the information from NASA. So what we have for a project is his using the information from the Kepler-2 project, using models for radial velocity and other orbital aspects, determining mass and spectroscopic analysis, has produced this or found for us this rare possible previous core of a Jovian type planet in orbit around this star. And it is on my take on that was worth an award that we are presenting with him. Okay, I would like to say any questions. I'm not sure I can answer any.
I have one.
This was really first-rate work.
Can you remember if his data mining was done using Python scripts?
Yes. That was one of many.
Yes.
There were a number. And I wanted to list all the different things he used and whatnot, but I think would be unfair to our speaker tonight if I spent too much time on that.
Yeah.
So I want to shift.
Thought you were going to have her go first.
Right.
Using the chat feature here, could you send me what school he went to? He's going to now as a senior, and I know he's going to Columbia, but forgot what area of study.
Okay.
Or email.
All right.
Thank you. That concludes my questions.
Okay. Now, when I encountered Katie's project, it was like, oh my gosh. First of all, I have done asteroidal occultations and I've done grazing lunar occultations, and I just was so pleased to see something that was really in my wheelhouse. But that is not, but my dealings with this were years ago, when we used tape recorders and recorded sound signals from WWV and gave verbal or using a noisemaker signal for the on-off events that you observe during these. And in a conversation with Katie, I did ask her how she did her timings on this or integrate the timing with the actual event. And I think it's better that Katie will explain that to us. But this was such a great hands-on and opportunity to do real science and something that we as amateurs can do too. And so without further ado, I want to turn it over to Katie. And if you could tell us a little more about yourself and how you got into this. And I'm glad to have Rick on board. And Rick, if you need to jump in here anytime, please do. But Katie, if you could unmute yourself, and we'll turn it over to you.
Hi, I'm Katie. I'm a sophomore at Sacred Heart in Greenwich, Connecticut. And I became interested in astronomy. Well, I think my parents introduced my brother and I to astronomy when we were younger by taking us to observatories on weeknights. And like wherever we went on vacation, they would find an observatory somewhere to take us. So when I entered Sacred Heart, I knew I wanted to join the science research program because I like science, and I knew that I wanted to do something that had to do with astronomy. And since Sacred Heart has an observatory on campus, I thought it would be in my best interest to use the resources that my campus offered. So I spoke with Mr. Bria when I was trying to figure out a project that the observatory on the campus was capable of, and asteroids were always something that I was interested in. So when he mentioned that asteroid occultations were a good opportunity and starting point for research, I was very interested in using that as a project idea. I have some slides that I made for better viewing. Is it okay if I share those with you?
Absolutely.
Okay. Can you see my screen?
Yes, indeed.
Yes.
Okay, great. So my project was called Uncovering Abnormalities in Asteroids using Asteroid Occultation. And the purpose of the study was basically to determine the shape of asteroids using occultation analysis to potentially discover an abnormality. And so occultation, I don't know if everybody knows, but just it's when a solar system body, in this case an asteroid, passes in front of a more distant body like a star, temporarily hiding it and blocking its light, and it's the drop of the magnitude of light that is measured. So some examples of abnormalities include an asteroid with a moonlet, binary asteroids, or also a contact binary asteroid. But there are different abnormalities that could be found. So the hypothesis of this experiment was that asteroid occultation can be used to precisely discover any irregularities, because the blocking of light when an asteroid passes in front of a star gives information about the precise shape and size of this asteroid, and this data can be used to determine if there are any abnormalities in the shape of the asteroid. So when I decided to start researching asteroid occultation, I was very interested in the significance of studying it. And I believe that it is very important, even though it may seem like something that can be done. It doesn't require such high-tech telescopes and cameras as maybe some other techniques in astronomy do, but it is still very important because it creates opportunities to study the nature of objects in space and discover characteristics that have been previously unknown. And it also opens up a very widely unexplored field of study to learn and discover new techniques. And also, there are the more interesting ideas, such as an asteroid that could potentially strike Earth. And although it's unlikely, the devastating consequences imply that we should probably be very closely studying these different types of asteroids to understand their trajectories and compositions. And also, asteroids are the building blocks of planets and can help astronomers trace solar system evolution. And so it is very critical that we can study the compositions and structures of the asteroids to learn about them as well. So there have been studies done before on asteroid occultations, and I'm not going to go through every detail of the studies, but I read some articles before I began my research, and the articles kind of lay out the idea that occultations and other methods, such as asteroid photometry and using the diffraction of radio waves, have been used to determine shapes and size of asteroids and to determine any abnormalities. So my research, I kind of aim to take this technique that has been used previously, but to add on to it by further improving the precision of asteroids that have already been measured, and also maybe determining something new about an asteroid that has not been measured very well. So, methods. So for the occultation procedure, I was grateful to have Mr. Bria from the observatory at my school help me out with this project. And at the observatory at my school, we used a planewave 14-inch telescope and a Wattec 910 HX camera. And then we also used video time inserters, which inject timestamps into every frame of the camera. So it helps, like very accurate timing when you're analyzing the data. So some of the procedures we used was you want to locate the target star, and our observing site in this case was the observatory at my school. And then getting all the computer programs and material ready. So like PIO and the Cult Watcher were used. And I believe PIO is a Python-based program that has only been developed fairly recently and is rapidly developing even now and continues to be updated. So it has extremely accurate and precise analysis and information. And we recorded test videos to determine any personal equation of error, and then began continuous observing and kept observing until 2 minutes after the event's estimated time was, in order to determine if there were any abnormalities or anything like that.
Katie, Katie,
yes.
can I interrupt you for a second?
Yes.
Does everyone understand what this is showing us here? Because this is really the key to it. Each one of these lines represents a different observer. And I assume that's correct, yes?
Yes, yes.
Okay.
Yeah.
So you get the data the same way you would get for a total solar eclipse, say. And you have to be on a certain line to see the whole sun occulted by the moon. You know that if you are at right angles to the eclipse path, that will diminish or affect the totality experience you have. Well, we're not talking about a disk here. We're looking at what is, for all intents and purposes, a true pinpoint of light as the star image. So if you have, this would be the center line for the totality of this asteroid, and observers situated geographically at right angles to that line will get these different views. Now, we're talking about spacing of what, probably only a few 100 yards, maybe?
No, much bigger.
Much
No,
bigger?
in our case, it was much bigger.
Okay.
In our case.
It could
Okay,
be,
good. Thank you
it
for
could be
that.
miles. I'm
Yes.
a member of IOTA as well.
Oh,
And
good.
these things are called tracks, and they could have observers anywhere along the path, and sometimes multiple observers to deal with potential equipment failures. But what the paths are giving are, for an unknown, potentially unknown object, size, shape, and potential mass and spin, gives us the idea of the size and how potentially its spin rate by having different observers along the path do these timings.
Oh, okay. Yeah. So along both axes, you've got differences in measurement then.
Yes, indeed. And
So
now
is
they
each of
standardize
those,
that equipment too, so that every observer is going out with the exact same equipment.
sorry, is each of those lines, does each of those lines represent the same star being occulted?
No, they're
Yes.
observers.
Oh, well, okay.
Well, yeah, but what are they observing? I mean, I understand they're observing.
the occultation of this asteroid as it passes in front of a star.
A star, but is it the same star that it's passing in front of?
Yes.
Yes, yes.
So
Because
the
asteroid's tiny.
yeah, no, I
It has to be
understand
the
that,
same star.
but the separation of miles seems enormous to have that kind of.
Same
Yeah.
thing with the solar eclipse.
Well, yeah, but the sun is so much closer. I mean,
Okay.
the angle of a tiny asteroid and a star that far away seems.
I don't want to take away from Katie, but
Oh,
as
help
it
us out.
as it works out, the size of the shadow on the Earth is the exact size of the asteroid, because the star is at infinity essentially. So it's a pinpoint. So
the
that's
rays
the
are
neat thing about the whole of process is the shape of this asteroid is projected onto the Earth in the shape of its shadow.
Ah,
So the
See
more
that-
observers you
okay.
have, in the case up there, it was probably 30 observers in that case, in that example of a card there.
Yeah.
You could determine the shape of an asteroid easily because you have so many observers. But most of the asteroids we were reviewing were about like 80 miles in diameter. So if you're 20 miles apart or 10 miles or a mile or two apart, it's fine because the asteroid is 80 miles across or 100 miles across, something like that.
Okay, thank you.
Well said.
I had no idea that was the case, and that's fascinating. Thank
It's
you.
a good question.
I'm working on a speaker for the fall.
But I will just say, and Katie, I'm sorry, I didn't mean to steal your thunder there.
That's okay.
The one time I was published in Sky and Telescope magazine was for my data line on an asteroidal occultation. This was years ago when the word was getting out, except I didn't get a hit like this. My line showed no break at all, but it was so close to the limiting edge of the asteroid, they included it because it established the limit, I guess.
Boundaries. Yes.
Oh. Okay,
Yeah.
Katie, I'm sorry. So I just want to make sure we all were on the same page as to what we're looking at here.
And remind us all to mute except Katie.
Thank
No,
you.
that's okay. And it's actually interesting that you brought up the limit because that's another interesting thing about asteroid occultations, that even if you get a miss, your data isn't useless. It's actually very valuable because it does tell the astronomers and the scientists where the limit of the asteroid is. So it's valuable even to get a miss. An alternative approach to asteroid occultations is asteroid photometry, which measures the rotation rate of asteroids based on light curves. And the reason we didn't go with this approach is because it takes a lot longer. The IOTA already combines this information with occultation data to create these shape models. And also new software would have been needed at the time of when I started my project. Okay, so some results that we got. So the first asteroid that we viewed was on April 13th, asteroid Jacqueline. And as you can see from the graph, it did not occult. And the way you can tell this is because in the graph, you don't see any noticeable dip in brightness. So this graph, what you're seeing is the x-axis is basically just the time frames, and each dot represents a separate frame that is being viewed by the camera. And the y-axis is the measure of and the fluctuation of magnitude of this star. And as you can see, there's no noticeable dip in brightness. So there was no positive asteroid occultation.
Katie, what is the magnitude range here? What magnitude are we talking about?
Well, I think it's different for each asteroid. I don't have the exact data with me on this particular asteroid, but for a lot of the occultations, the estimated dip was not even that much. It was usually around, like sometimes it'd be less than a drop of like one point of magnitude. So it was difficult to see it sometimes. And I know you see these numbers of 200, 400, 600, 800, but those are more like generated numbers. They don't actually mean that the magnitude was that high.
You see, we can't read the numbers. That's why I'm glad you just said them.
That's okay.
And what are they on the x-axis?
100, they go by hundreds, I believe.
Mm-hmm. You've got here image of target and tracking star. We never had the luxury of seeing the target. We only saw the star and set up and hope something would happen. So I'm assuming the asteroid's magnitude is probably quite faint.
Yes.
You know what
Yeah.
the number was? Was it like 14, 18?
I can't recall from this particular asteroid. I could probably
Okay,
go
that's
back
okay.
and look, but yeah, so the target and tracking star, basically what we had is you had one target star, which is the star that you would want to have this dip in brightness, but then you'd also have a tracking star, so you could compare the magnitude of brightness in that star, because if they both dip, then it could have just been like some sort of outside influence, or like the twinkling of the stars or some clouds or something. But if only one of them dipped, then you would be more likely to know that you had this abnormality. And I believe in this graph,
I'll jump in real quick here though, just to let them know the Jacqueline event. The star was magnitude 10 and the asteroid was magnitude 16.
Oh,
But we didn't get
okay.
a positive anyway, so it didn't matter. But anyway,
Okay.
just to let you know.
Thank you.
Sorry about
no, that's all right. Yes, so just this is a different asteroid, which I'll get to later, but in this graph, you can see the green would be the tracking, the tracking star, and then the red would be the target, and neither have a noticeable dip in brightness. So you can assume that there was no positive occultation. So that was asteroid Jacqueline. That was the first one, and it did not occult. And now the second asteroid that we observed, asteroid Walpurga, was on April 20th. And it did actually occult. And as you can see in this graph, there is a noticeable dip in brightness, which means that it did occult. And here, after sending our data to IOTA, combined with the photometry data that they use, an image is created of what Walpurga most likely looks like using the different observers. And as you can see in this event, it seems that there were 4 observers. 2 did not hit the asteroid, but as we noted before, that is also important because it tells you where the asteroid is not. And 2 of the observers, I think one of us was ours was one of those included, got hits of the asteroid. So they kind of created a shape based on previous data and our data, and then photometry data. And although there was no abnormality in this asteroid, the most previous data was from 2017, before all the software has been updated, and they had much larger error margins, and they used 16 frames. And as I mentioned before, each dot is an individual frame, and what you want is fewer frames, because then each dot shows a smaller amount of a second, which means that there are more, that you see more precise data, because each one is of a smaller fraction of a second. So you see more parts of each second than if you were to have more frames. And so since we had fewer frames, our data was a lot more precise than the most previous data as well. So the third asteroid that we viewed was in October, and it was asteroid Chandra. And it did not occult. And as I mentioned, you could see the comparison between the tracking star and the target star, and there is no noticeable dip in brightness. So there was no occultation. And then on December 15th, we viewed asteroid Lanzia. So asteroid Lanzia did occult, and what we noticed after we were analyzing the data was not only was there one large dip in brightness, but if you could see afterwards, there was another dip in brightness. And this dip in brightness was really interesting because it went, almost down, pretty much down to where the first dip in brightness went in magnitude. It dropped a very similar amount of magnitude. So it seems unlikely that it could just be from some outside influence or some cloud or twinkling of the star, because it was such a significant drop in brightness. So after a lot of correspondence with IOTA and correspondence with IOTA and looking into other previous occultations that had a similar double hit, we came up with IOTA, we came to the conclusion that the most likely possibility and probability of this double hit is that the asteroid has an abnormality of a concavity. So when they created the image of Lanzia, they did not create it with the concavity originally, because originally they couldn't figure out why that there was a double hit. But so this image that you see here is actually an image that we created based off the image that IOTA originally had. So this concavity is what the most likely possibility of what this double hit was. And how we came to this conclusion was from a article of Science Journal article that IOTA provided of a similar occurrence from another observer on a different asteroid, asteroid Taurus. And they found, if you can see in this graph, they had a similar instance of this double hit as well. And they had 3 likely conclusions of this, that it was a 2-body double asteroid, a contact binary asteroid, or as this graph on the right, or this drawing on the right shows, a possible concavity. And what they came to the conclusion was that it was most likely a concavity. So combined with this information and the recommendations of IOTA, we determined that the most likely probability was that this was a concavity. And this was something that hadn't been discovered previously, and this was the first ever discovery of this particular abnormality on Lanzia. So the final asteroid that we observed was asteroid Marlou. That was at the end of December. And so as you can see, there was no noticeable dip in brightness in this asteroid. So it was a miss occultation. And here you can also see another kind of close-up of the target and tracking stars. And the numbers that you see at the bottom are from the video time inserters that we use, which basically just show like specific timestamps for every frame that is taken. So as I kind of mentioned before, the graphs of Jacqueline, Chandra, and Marlou represent miss asteroids with no dips in brightness, and data was limited due to weather and availability of observers. And then the graph of Walpurga showed a large dip in brightness, which indicated a positive hit in the asteroid. And although there were no noticeable abnormalities, we did improve the precision of the results. And then the graph of Lanzia contains a double dip, meaning that the star blinks out twice, and this indicates an abnormality in the asteroid. And the most likely conclusion, which we determined, was that it is a concavity, which could mean possibly that a projectile could have hit the asteroid, creating this concavity, or even another possibility is that maybe multiple asteroids are fused together, creating this kind of uneven surface and this concavity. But those are just 2 possibilities that further research would need to be done to determine. And then, so just in conclusion, asteroid abnormalities, such as the one discovered in Lanzia, can reveal the origins of such celestial objects, such as these collisions with projectiles or other asteroids. And it's really significant to improve the precision and accuracy of occultation measurements in order to provide important data to scientists studying space and scientists that could potentially want to study asteroids to determine their origins, or also for possible mineral mining in the future. So knowing their shape and composition is also very important. And then in the future, asteroid occultation research could be done on more asteroids to search for more abnormalities and to continue to improve precision of measurements, or on other celestial bodies, such as exoplanets or any other celestial bodies. So yeah, those are my references, and thank you all for listening. I can unshare my screen.
Thank you, Katie.
Yeah, thank you.
Back in the old days when Scott was doing occultations, they used rocks and chalk marks on the cave. Notice the timing.
No, we used, for those of you Star Trek people who were back into the original Star Trek, We used stone knives and bear skins, actually.
Yeah.
Yes. Well, thing is, between his occultation
And we were
timing
grateful.
and when I joined IOTA, the timing kits, you remember you had to build the timing kits, Scott? Back
I
then?
was just, I didn't even do, I was just told we did it with a tape recorder and
Okay.
that
That's
was it.
even older
The
time.
video.
They created a standard timing kit and wanted you to do something like a nighttime security camera. But those parts weren't available, and if you had them, fine. If not, you didn't. Now they're standardized on something depending on the size of the asteroid and the distance and all that, like a C11 with a hyperstar and a QHY CMOS camera with embedded GPS and timer chips that would embed the signal with the timing clock tick, if you will. And if it's a smaller or a larger possible occultation, then they went down to something like a, believe it or not, a Skywatcher 8-inch Newtonian. And there are like half a dozen IOTA members that are trained enough to travel around the world, unlike those who have a itty bitty little plane wave and a WATEC in their back pocket that are in a fixed observatory and can't go anywhere. These people are certified enough by both IOTA and NASA that they'll travel to South America or Europe or places of that nature, and they actually get their names credited in with the scientific research as just doing an occultation timing event. My friend Chris Erickson is one of those IOTA style people, and of course, he has the big ass the large hyperstar module that goes on the front of a Schmidt Cassegrain, specifically Celestrons, the C11s and the C14s, that make them an F2 telescope. And then the QHY camera sits on the front end of that. That's not something you want to drag, more than a few hundred miles with you, but not across the, continents.
There's a guy that travels with a C14 and goes to
Sure.
occultations. It's just, the word certified is right. They gotta be
Yeah.
something loose up there, but
Yeah.
that's dedication.
My friend
we stay still and we let the asteroid come to us.
Yeah, my friend is Chris Erickson, if you know him. He's out in the west side of Hawaii.
I seen the name.
Yeah.
Well, the satisfaction that I had from the equipment that I used was I was using an 8-inch f6 Dobsonian, and I had ground and polished the mirror myself. And that was, but I didn't have all the other gimcrackery that has involved since. I'm just curious, Katie, is Dave Dunham still around? Does that name still come up from IOTA? You're muted.
Yes. Hey, he and his wife are the ones that will travel to South Africa
Okay.
for they have, and they haul a 16-inch Dob, and they'll do events like that are teamed up with NASA. They did the Pluto event, they did the Apophis event that teamed up with NASA because NASA. Oh, they did the New Horizons went to that. I forget what the name of that.
Thule?
That dwarf.
Thule.
Yeah, they did that. Yes, they did that. Yep.
Asteroid Thule, that was amazing.
Right.
Yep.
No, they're like royalty of IOTA. I'm sure I don't have to tell some of the IOTA guys that, but the Dunhams. The Dunhams actually got me involved at a NEAF meeting. They did a presentation, and I said, "Wow, that sounds like interesting. Something interesting to do." But I was telling Katherine of the primitive, compared to what we do now, the primitive methods that were used back then, and just to give her an idea that we're kind of blessed to what we have.
I want to bring it, Katie, could you just unmute for a
What
moment?
our video time inserters and stuff.
Yes.
So, what looms on the horizon for you? I mean, this is just wonderful. I've smiled through your whole presentation because it brings back such memories and that opportunity to get involved, get your hands on stuff. So, what looms on your horizon at this point?
Um, that's an interesting question. I'm very interested in continuing. I still have 2 years left of
Mm.
high
Wow.
school and of the science research program, and I'm still interested in continuing with astronomy. And actually, I was doing some reading, and my dad actually forwarded me some interesting articles about the field of exoplanet climatology
Hmm.
and how that could be used in creating these models of climates could be used to determine like if what makes a climate habitable for an exoplanet and how can that be compared to Earth's climate today, and also maybe something could be found to help mitigate global warming on Earth today. So that's definitely one of the avenues I've been starting some research on. And then yeah, I was interested in exoplanets. That was one of my original avenues that I was interested in, but I thought asteroid occultation would be a good starting point. And the technique is also very good and could probably be applied to exoplanets and other celestial bodies. So most
Radial
likely,
velocity.
yes, yeah, most likely I'll probably either do something continuing with asteroids or maybe shift over to exoplanets. But uh, I haven't gotten far into that research yet.
Well, you really are here. I mean, you couldn't be into this at a better time. We're at
Oh
the
yeah.
threshold of sensitivity and detectability of so many of these things. I mean, the idea of even being able to measure an exoplanet's atmosphere was a way out there discussion only a few years ago. And I think you will find if you tend and you pursue this and you get into atmospheres, of course, you're going to become face to face with the biochemical implications for
Mhm.
what you encounter. A parallel pursuit you might want to look into is some of these studies about extremophiles and the kinds of life. The term life begins to get fuzzy by definition. Uh, I mean, we've talked for over a century about how life can live in the hot springs of Yellowstone and all the bacterias and the cyanobacterias and stuff in those hot springs. But now they're finding chemistry that replicates under all kinds of pressure and temperature and parent star radiation and all that stuff. So yeah, it's a good time to be aboard. I look forward to you presenting at a future meeting.
And just think too, you don't have to have this massive observatory telescope and camera. As I mentioned, some of the stuff that the IOTA standards eyes on are simple 8-inch Newtonian reflectors, just a few $100s, not thousands and thousands of dollars for a 12-inch plane wave. And we're talking a $500-600 telescope plus the standardized camera.
Yeah.
And they standardize the laptops too. So
I
you can
just want to
do it.
shift tracks for just a moment because I don't want to forget to mention. I mean, I've been judging for over 25 years, which is hard to believe. We feel old, but I think Katie is the youngest senior. I don't think we have had a sophomore science project to be honored.
One.
This is one. Okay.
One.
So you are in special. We are in special company indeed. So, well, that's great. I hope I know that geography separates us a bit, but I'm looking forward to when we can get back to face meetings, and I hope you'll be able to drop in. Well, I hope you could drop in on all of them, but if you could drop in on a few, and bring that guy, what's his name, Rick, along with you. That would be great.
Yeah. Yeah,
But
and
thank you
I
so
got
much.
I got to say for me, I'm impressed and humbled. I mean, I'm still at the stage where I just go out in my my driveway, and I'm impressed just looking at the Orion Nebula. So, you guys are all a lot of what you guys are talking about is way beyond me, with the equipment. You guys have been out there for years. using.
Yeah, but you'll
So-
still leave
so-
this meeting with more than you came here with, right?
Absolutely, absolutely. That
Happens
was
every time.
Katie. Thank you for that presentation. That was terrific.
And it's
And
hard, if one of you know more about radial velocity for exoplanet research, go back into the archives of the ASGH news group.
Hmm.
In the last month and a half, I've had radial velocity talks posted in there, and I do
Yeah.
believe one of them came from Hawaii, from a researcher or postdoc at Keck.
Well, Katie, you no doubt are going to be recognized in many ways for your many talents down the future, but I think that you will always find the ones that you cherish the most is the recognition from your peers. And I like to think that you'll get to enjoy that numerous times as you put your path in life together.
Yeah.
So,
Thank you
Okay.
so much for having me. It was a great opportunity and one that I, like a year ago, would have never imagined having. So thank you so much.
well, big
Thank you,
thanks
Katie.
to
Thank you.